Hello and welcome. I am Beth Mashesky, Senior Scientific Specialist at the Illinois Sustainable Technology Center, which is part of the Prairie Research Institute at the University of Illinois. This webinar and all of the Illinois Sustainable Technology Center's webinars are certified green events through the University of Illinois Institute for Sustainability, Energy, and Environment. To find out more about certified green events through U of I, please visit sustainability.illinois.edu. To find out more about the Illinois Sustainable Technology Center's webinars, please visit istc.illinois.edu/events. A few housekeeping items before we get started. You can download the slides in the handout section of the GoToWebinar toolbar. Today's webinar is being recorded. The recording and slides will be available for viewing online within about a week. I'll be emailing out the availability of those to everyone who registered. And then everyone will remain muted for the entire webinar. You can type in your questions through the GoToWebinar toolbar, and I'll be reading those to the speaker at the end. So with that, I'm very pleased to welcome today's speaker, Jeff Spangenberger. Jeff is the Materials Recycling Research and Development Program Lead in the Applied Materials Division at Argonne National Laboratory. His program works to solve materials separation, recovery, and recycling challenges, resulting in cost-effective and environmentally sustainable processes that are then transferable to industry. Jeff is also the director of the Resale Center, an advanced battery recycling program funded by the Vehicle Technologies Office of the United States Department of Energy to evaluate and advance the cost-effective and sustainable recycling of end-of-life advanced batteries. So Jeff, thank you for joining us, and the webinar is yours.
Thanks. Excuse me. Thanks, Beth. Hey, I don't know if it's better to have the video on or video off. Do you have a preference?
That's entirely up to you.
Okay. Well, let me do it this way. I'll turn the camera on for now, just so people can see me just during this opening slide, and then I'll turn it off so you don't have to look at me so long. So thanks again, Beth, for the introduction. Excited to talk to everybody today about lithium-ion battery recycling. You know, it's a pretty up-and-coming area, and it's pretty exciting to me. Hopefully, I can encourage some of you to get maybe a little more excited about it. Maybe you're already really involved in it. So I think actually Beth did a great job on introducing me and my background. So I'll just skip past this slide and turn my video off so you guys don't have to look at me the whole time, and you can focus on what I'm saying, but at least now you know what I look like. Let's see, next slide. Good. So I like to set the stage in the beginning of my discussions. And if we look at the chart, I think this is a chart of electric vehicle batteries at end of life. So when they reach the end of life, you know, how much is coming back? The y-axis is million metric tons, and the x is the years. And you can see that there's great growth. But what I like to point out is actually the fact that this chart, which starts at 2025, is not even today. So we're still, at this point, 4 years away from that. We're just a blip on this chart. And so really, from today moving forward, we have tremendous growth. We also have tremendous opportunity to improve the processes, the infrastructure that we currently have to make this a better endeavor. Let's see. So I guess real quick, I'll say that this is EV, electric vehicle battery volumes being shown here. They're predominantly going to be the biggest amount of battery uses, even compared to stationary applications and consumer electronics. I should refresh this with a slide that includes those two. So let's see. There are differences in the batteries. Lithium-ion batteries, one lithium-ion is not the same as another. The consumer electronic lithium-ion batteries, like in your cell phone and in your computer, use a chemistry, typically we refer to it as LCO. The C is cobalt, and so there's a lot of cobalt in it. There's a lot of value there. And you probably all have some batteries sitting in your desk somewhere that you just haven't turned in yet. And you can actually make money by turning them in and using the current technologies that are out there today. The problem is collection. There's not that many batteries that go back. People don't know what to do with them. They don't know where to bring them. Things like that, or they're integrated into your cell phone, and so what do you do? Geez, I don't want my information to get out there. So if you're anything like me, you have like 5 cell phones stuck in your drawer. It's kind of like a museum. And then there's also the stationary application side, and this is going to use batteries that are different technologies, different chemistries than the consumer electronics. Consumer electronics, you don't want to have a heavy weight in your pocket, so they want to use real light, energy dense batteries. And so in stationary, you can have a lot more weight. You're not worried about energy density as much, so you can use some cheaper materials, and that's good because it's lower installation costs, but it's also bad in that the value of the material at end of life is lower. And so it turns out it's probably going to cost you money to recycle those batteries at the end of its life. So you need to take that into account when you're installing a stationary application with battery storage. And then EVs are somewhere in between. EVs, I guess I can say, let's see, they started coming out with lithium-ion technology around 2012, say. So Chevy Volt, that's the plug-in hybrid. The Tesla Model S came out around then. The Nissan Leaf came out around then. There were not that many of them sold. I'll say in the tens of thousands were sold in the first, couple years. Those vehicles have 8 to 10 year warranties on their batteries. So 2012 and 8 years is 2020, 10 years is 2022. The warranties on the batteries in our electric vehicles that were first purchased are just starting to come out of warranty. And that means we'll start to see some coming out of end of life. But that's why we're just the blip now, because they're still new vehicles. In fact, a vehicle averages 11 to 13 years. My truck, secretly, again, don't tell anybody, is 18 years old and it's still doing great. So, it's going to take a while for these materials to actually come back to be recycled. But at the same time, just like stationary, we don't put LCO chemistry in our cars because it's very expensive. And so the value of the batteries are fairly low at the end of their life. And so I'll get more into that in a few minutes as we move on. I also want to point out that recycling is critical to the material supply chain for our lithium-ion batteries. We don't have enough cobalt, essentially. We can always dig deeper, but it's really the amount of cobalt projected that's required for these batteries really digs deep into the amount that we have available to us in this world. And so we need to make sure that we recycle in order to have these materials. So that's my long setting the stage slide. Let's move on. So you can, as I mentioned, currently recycle lithium-ion batteries, and very effectively. All of the processes that are out there now are better than digging the materials up and refining them and putting them into batteries and throwing them out. So we want to recycle lithium-ion batteries, if not just for the supply chain issue that I talked about too, but emissions are much less. A lot of the materials come from sulfur-based ores, and so when you produce them from the ground and refine them, you produce a lot of sulfur emissions, and that's problematic. When you use once you've gotten the sulfur out, when you recycle that material, you don't have that emission. So recycling, again, is a great environmental opportunity. So let's see. The processes are pyro-based and hydro-based, and I'll refer to that a few times through this talk. But pyro basically means fire or heat. Hydro is aqueous solutions, so acids typically. Yeah, I'll wait. Well, I'll tell you now. So pyro, you're going to take your battery, you're going to throw it into a furnace, you're going to burn the organics. You get that heat, which is great, but it's gone now. So things like your solvents in your electrolyte, your plastics, carbon, graphite, that'll all get oxidized. Consequently, the lithium in the lithium-ion battery in a smelter goes then out with the slag as an oxide, along with the aluminum, and now it's really difficult to get out. So that's a disadvantage. There are plenty of advantages for pyro, though. But what you get out then is this nice alloy of really good metals, the cobalt, the nickel, the copper, things like that, and other metals that might be in the feed of the smelter. Sorry if you guys hear noise in the background. My kids are just coming home, or one kid is coming home from school. So that's pyro. Now the alloy, actually, I should mention, has to be refined so you can separate the different metal constituents into separate streams. And so a lot of times, actually, ironically, you use hydro after the pyro step. In hydro, what you do with a battery, anyway, is you shred it up to liberate the materials, put it into an acid, dissolve the metals, filter out the rest, and then you individually precipitate out or separate out the different metal constituents. And typically they're metal salts, which are lower valued materials than the cathode that you just got them from. And that's typical. It's great because we can put them typically back into our batteries. And so we have this closed loop circle, and that's great. So there you have it. The key word here is low value. The US is trailing other countries. Asia, Europe, way ahead of us. We're lagging. The government is aware of that, and we're working now very, very hard to try and play catch up. And it's very important. It's important to know that we don't really we don't produce a lot of the materials in batteries. One thing that we are good at is making batteries. We have the Gigafactory, Tesla's place, and that, all they do really is assemble the batteries there. They put them together. We don't have a lot of the materials here. We don't produce them here in the United States. And so we rely on other countries to provide us those materials. And that is not a great position to be in. It takes us back to reliant upon other countries for our oil. And so we just don't want to be in that vulnerable position. And so we need to ensure that we have a strong, resilient supply chain, and recycling can help enable that. So the Resell Center was established as basically an advanced battery recycling group, I guess you could say, that is working towards, and I'll show you in the next slides, cost-effective battery recycling. It's led by Argonne National Laboratory, which is where I work, but it also includes the National Renewable Energy Laboratory and Oak Ridge National Laboratory, and then we have 3 universities as well. And I think the interesting thing on this slide is the fact that we had our ribbon cutting, and that was back in February 2019. So we're about 2 years old now. But what I found was that the news, so there's some PR that's put out about this kickoff, but the news made it around the world. I put up some of the New York Times, Japan Today, Taiwan News, South China Morning Post. So it made it around the country and so around the world. So it really hit home to me just how global this topic is. So the Resell Center's mission is to decrease the cost of recycling lithium-ion batteries. That's the, like I should underline that, decreasing the cost of recycling lithium-ion batteries. And that is to ensure the future supply of critical materials, a hot topic these days, and decrease energy usage compared to raw material production. I have this picture in here because this is where vehicles come to die. Actually, I should say be reborn. Because it is a very circular infrastructure. Many of you may not know that our vehicles are one of the most recycled consumer products that we have. At the end of its life, it hits one of these places, what you would call a junkyard. Auto recycler is what they prefer, dismantler, and they pull the parts off of the vehicles for resale. So it could be body parts, it could be an alternator for remanufacturing, engines, anything. After they also drain the oil and take out fluids, they decontaminate it essentially. Then it goes to a shredder, and the shredder shreds the car into fist-sized pieces and removes the metals from it. And it's a great system. Everybody makes money. My 18-year-old truck right now, even if the wheels fall off and the engine blows up, I can get $150 for what's left of it, and that's great. If it right now, if it has a battery, that causes some economic challenges to that. I'm not going to get my $150. In fact, I may actually even owe a little bit of money to have that car processed. And so, to me, addressing this cost of the battery recycling is really where it's at. Like I said, recycling, no matter how you do it, is of great benefit to the environment. If we can just have an incentive to really make this system work, we need to drive the costs down to process these batteries. And so anyway, there you have it. So the Resell Center, the hope, I have the purpose, but really the hope is to foster the development of cost-effective, environmentally sound processes to recycle these, and really to bring people together from all around the country, all around the world, to bring their piece of the puzzle. I always talk about this, and I assume people get tired of me talking about this as a puzzle, but so be it. There are a lot of, there's a big picture that needs to be put together for this all really to work. And there are people working around the country and around the world on little bits of this process. They may work on relithiation, which is, I won't go into what that is, but they're just focused on relithiation. Or they're into material separation, things like that. But we need to get everybody together to put these puzzle pieces together to make this big picture. And I'm hoping that the Resell Center is a platform, and so far it's been great, getting people connected with their ideas, their concepts, and getting this picture put together more efficiently. And then all the great stuff comes, right? The reducing the use of our limited resources, reduce energy consumption, increase our national security, bolster our supply chain. And really, at the end of the day, what we want to do is drive the cost of batteries down, because I don't have an EV yet. They're too expensive for me. So we want to make EVs more affordable for everybody. And with better economics on materials, on battery recycling, we can create cheaper materials for batteries, and that will help lower the cost of batteries. Not only that, so now you and I can buy electric vehicles. It allows the grid to have more energy storage in it. And so now the wind can be used, that energy can be used around the clock, and the sunlight power can be used, or energy can be used around the clock. And so we actually have a greener infrastructure, a greener energy supply for these electric vehicles. So it's just a win-win when we drive these prices down. So along the same lines, the yellow pie piece here is RECELL. You can see the universities, Michigan Tech, UC San Diego, and Worcester Polytechnic Institute. We have the red pie piece, which is also a Department of Energy funded a program. And that's more about the collection, the transportation, and getting the batteries to the recyclers. And then there's also a program that, because cobalt is where a lot of the expense is, reducing the amount of cobalt that goes into batteries. And in fact, there's advantages to adding things like nickel. You can have higher capacities. And so, so that's the third pie piece. All in the central core, the goal is to lower the cost of lithium-ion batteries. I want to take a moment also to go back and say, with the current recycling technologies that are out there, the products rely on the metal salt values. So you have cobalt sulfate, say, that's a great precursor to go into, a great raw material to go into a battery, nickel sulfate, things like that. And so if we remove cobalt, the expensive material, from a battery, then we remove the value of that battery at the end of the day. Now, we don't have lithium iron phosphate batteries in our vehicles because they're lower energy dense, but they are being used in other countries that have different needs. Recycling lithium iron phosphate is a huge challenge because there really is not much value in the products that you get out. The raw materials that go into it are very low. The cost is of the cathode material is lower than others, but if you recycle it, basically there's not much residual value. So it's a great challenge. So that's something that I look at with the current technologies of hydro and pyro, and I will get into direct cathode recycling in a minute as far as how that can change that. So we have 4 focus areas in RECELL. There's, as I just mentioned, direct cathode recycling. There's the recovery of other materials. I hate the name of that, but I can't think of anything better. If you can think of something, please let me know. The idea here is a lot of people are focused on the valuable metals, but what about the lithium salt in the electrolyte? What about the plastics? Is there any value in the plastics? If you can do anything with those materials, you can kind of get a little bit of value out of this and a little bit of value out of that, and it all adds up. Even if you break even, that's great, because now we don't need to get rid of it as a waste. So we're looking at that. Design for sustainability is really important. The fact that we can change things now to make our batteries more recyclable, greener, less carbon emissions in the manufacturing of, all that is great stuff, but it's a really hard focus area for us because change is difficult. And I'll challenge you to look at any product on your desk, in front of you, in your car, wherever you are. What products do we have that are designed for recycled right now? Or designed for sustainability, sure. Our milk cartons are getting thinner. I just noticed that the straw at the fast food joint was thinner. But really, who does that, right? And so, but it's a great opportunity. So I'll stop there. Modeling and analysis are important things that we use, tools we use. We have a model called EverBat, which I'll talk a little bit more about in the end of this. We also have Libra, which is out of the National Renewable Energy Laboratory, which is a supply chain modeling effort. And we use those models to make sure that the work that we're doing is going in the right direction, The materials that we're going after are most critical. And also, you know, with Everbat model, we run every project, essentially every project, through the Everbat model to make sure that the cost and environmental impacts are going in the right direction. We don't want to work on a project that doesn't result in a process that's worse environmentally speaking. So a little bit more about direct cathode recycling, or more briefly, direct recycling. When you do pyro and hydro, and this loop diagram is a little bit wrong. I'm going to assume that you can see my cursor. But basically, well, first off, if you don't recycle, you're going to mine the materials from the ground. You're going to refine them, make them into battery materials, make your batteries, use your batteries, and then throw them out. You may get a second life out of it. And I'm not going to talk about second life today. But you enter recycle, and like I said, all of these are better than following that blue path and then throwing them out on the red path. Pyro takes the material all the way back to a metal. Now, let me step back a second and say all of these processes, cathode production, it's a very precise chemistry. These are you want to have a material that the lithium can shuttle back and forth easily, and so there's a lot of science and processing involved in making cathode materials. So at the end, what they do in pyro is basically you melt it down to a metal. Then you have to go all the way through the process again of making it into a cathode material. Same thing with hydro. You're going to get a metal salt back, and then with those metal salts, you need to go all the way back through the cathode manufacturing process, which adds cost and time and materials and wastes. And so the concept of direct recycling is take the cathode out of the battery, fix it while it's still a cathode. Don't ruin the chemical structure that was all that effort was put into to make. Fix it as a cathode, and then put it back into the battery. It's a great idea. Of course, we're studying it. There are a lot of challenges associated with it, though, and that's why the Department of Energy is really involved in this. They've kind of they're trying to get a little momentum with it. What challenges can we tackle? What challenges still exist? Things like that, because the benefit is huge, and here's why. If you look at NMC, that's nickel, manganese, and cobalt. That's what we call the chemistry. LCO I talked about in the consumer electronics. So that's just lithium, cobalt, and oxygen. This is lithium, nickel, metal, cobalt, and oxygen. The raw materials that go into that chemistry is this blue bar. So let's say it costs $5 worth of raw materials to make, and we'll call this half, $10 worth of cathode material of NMC. So if our recycling process destroys this whole difference here, our revenue is going to be this $5 again. Then you can put $5 more back into it and make that cathode. Direct recycling says, or allows you rather, to recover this $10 back. And so your revenue can be even higher. It can be double. But as I said, there are a lot of challenges. One is 15-year-old car comes with a 15-year-old cathode chemistry. So what do? You know, we have projects to try and make old cathode chemistries work perform like more modern chemistries. We need very clean powders. So there's a lot of separation, intense separations involved. So, but we have more wiggle room to make this work. So, and if you look, I mentioned LFP. Look at this. The raw material value very low, but the processing cost to make it a cathode, the difference is huge. So, something to think about. To have a direct recycling process, I'm going to skip the processes of pyro and hydro really, but a lot of them are similar. We're going to shred the battery. So at the end of life, we're going to shred the battery. to liberate the materials, we need to do something with the electrolyte, and that's a solvent and a salt. The solvent is a low value material, but we have to get rid of it somehow, so we either throw it out or maybe we have a product that we can recycle. The salt is a higher valued material, one of the top 3 valued materials in a battery, so we're working on methods to recover the salt that can be then reused, hopefully back into a battery. After we get that out, we have to separate the anode and the cathode and the metal foils that are on those materials. If we just focus on the cathode, we still have carbon black and PVDF. Carbon black helps with electrical conductivity. PVDF binds the material together and makes it stick to what we call a current collector, so that we can take these electrons and have them push or pull through the system. We remove the carbon black and PVDF, whether it's recycled or whether it's destroyed. And then we need to do this relithiation typically, because we in the system, the cathode, when you make a battery, the cathode starts out with a lithium on it. And then when you charge it, it transfers over to the anode. So we need to relithiate that material, and then upcycling. So that's the idea of making it perform rather like batteries of today. So you need to have a step along all this circle working. If you have a break in this, it's not going to work. So we have multiple projects in many of these. If one can't perform, doesn't perform, we'll target. We'll have others that we can target to help fill in the gaps. So that helps reduce the risk. We're continually looking for new ideas, new projects to help, replace some of these steps, or not replace the steps, but to fill them in with operations. Another thing is that just like we steal a lot of technology from different fields, we're hoping that some of the technologies that we develop are going to help other recycling fields. Froth flotation is something that was used out of the mining industry for years and years. My past actually use of it was separating plastics with froth flotation. Here we can separate anode and cathode powders with froth flotation. We're playing with actually separating cathode from cathode using froth flotation. So what else can we do with froth flotation? So things like that. So the things that we can learn along the way hopefully can transfer to other industries. Manufacturing scrap is a great place for us to start the demonstration of direct recycling, and that's because it gets rid of some of the challenges that we need to address that will take more work to scale up, I guess you could say. So if we work with manufacturing scrap, we now don't have to deal with this 15-year-old chemistry. This is today's chemistry that we're working on. We also have the option of saying, I'll just take the cathode laminates. I won't have a battery. And so even that's even easier. So we're working with some companies now actually to demonstrate the direct recycling concept. And this is really huge because if you, like right now, there's a lot of waste in the manufacturing business of batteries. At every stage of the way. So there's, basically the powders can be mixed wrong, and the cathode, and I focus on the cathode here, but this is true with the anode as well. They could be mixed wrong. Once you get it into a slurry and you cast it, there could be streaks in your laminate. There could be maybe it's an uneven depth. Things go wrong, and so they get kicked out, and they're the amount total, even at the end, actually, let me stop and go a little bit further. Once they have the cell built, they format it and they check the performance of it. If it doesn't meet their specifications, they're scrapped. And so there are ranges, I've heard from 5 to 30% scrap generation from these processes. And it's very dependent upon how new a facility is, how new the company is. I think probably 10%, 8 to 10%. That's my, and I don't have any real reason to say this, but that's where I think the real scrap levels are for the average producer. That's a lot of material. So if you're going to sell that to a recycler, and or a lot of times they'll just take it off your hands for free. I don't think they'll charge you. It depends on what you're processing. But I mean, with direct recycling, you can take that material, you put it right back, you process it right there, you put it right back on the front of the line, and you keep going. And now maybe you can reduce your scrap from, say, 10% down to 5%. You just lowered your manufacturing costs. And guess who else benefits from that? You and me, because it lowers the cost of the batteries now. So it's huge. I think, let me see if my next slide, hopefully if I did this right, yeah, good, is a slide that my colleague Linda Gaines has put together. There's no data behind this, but this is the concept, is that this green line, top green line, is production of batteries, and it skyrockets, right? So this is the batteries taking off. Everybody gets an EV. We have we have this scrap. Now let's look at the end of life. That's the purple line. So it takes 10 years, here is where they say, before we start collecting the batteries. So we don't have any material to recycle for 10 years. So all of this has to be made with virgin material, unless we look at the scrap. The scrap, we always have some scrap, and this goes along the line. So just say that this is 10% of this value, the green line. We're actually going to have manufacturing scrap as our main feedstock for recycled products in this particular instance, and for like 15 years. Again, there's no real data behind this. We're filling this in now, but that's significant. And then if you add them together, you get this dark green line. And so this is the overall recyclability of material available. So manufacturing scrap is actually important to target right now. So there you have that. Everbat. Let's see, I'm going to try and move a little bit faster. Everbat is a model that looks at cost and environmental impacts of the life cycle of a battery. We have at Argonne BATPAC, which is battery performance and costing, and this is basically to make batteries. You can say, I want a battery that's going to go this far in this vehicle, and it says, okay, it's going to cost you this much, and these are the materials that you need. So then we take the bill of materials and we put it in to GREET, an Argonne life cycle analysis tool, and that says, well, we're going to have, with those materials, we're going to have this environmental impact from processing and manufacturing those materials. So we know what the cost and environmental impacts are of making a virgin battery. Right now, we don't have anything in the use phase, but at the end of life, we have to collect the batteries. There may be a pretreatment of some sort, but there's a cost and an environmental impact associated with that. Same with whichever recycling process you use. Depending on your recycling process, you're going to go through different routes, but basically you're going to have to make a new cathode, and you can put it back into a new battery. So now we can look at the cost and environmental impacts of batteries with recycled content. And that's pretty cool. So the output of this is very straightforward. It's this stage costs this much and has this environmental impact. And so like an example of how this can be used is to say, design for recycle, it's going to cost me an extra $1 to use bolts instead of weld this pack together. Nobody wants to do that, but you find out you can actually have $2 more net value at the recycling or pretreatment process, because now you just have a instead of a saw to cut open a battery pack, you can use a ratchet. I can't think of all the tools right now. So, but you get the idea. And so in the big picture, we're actually making $1. We're reducing the cost by $1. So it helps with that. You can also say, hey, I have a recycling process and I want to see how it stands up against others. We have 3 generic recycling processes, one for pyro, one for hydro, and one for direct in the model right now. And by the way, the model is free. If you go to search Argonne and Everbat, it's a free model. You can download it, play with it. It's Excel based, so if you know Excel, you should be able to your way around it. So you can model essentially, and when I say model, I mean your process has 3 components: a conveyor belt, a shredder, and a discharge conveyor. You put those in, and you say how much they cost, how much energy they use, how much labor it requires to operate that, and things like that. And I'll actually, in the next slides, I'll show you information like that, and it will spit out the comparison, right? So it's, of course, you have to have good information going in to get good information out, and that's not always easy to get. So anyway, but this has been a very valuable tool for us, and it's come in handy. This received an R&D 100 award in 2019. It's a new model. As far as I know, there's no other models like it that treat this whole life cycle. And in fact, we're talking now about actually including a little loop out here for the mining and supply chain aspect of it all. So some of the parameters that this addresses are labor costs. So you can say, I want to build this battery in Asia. I want to, I'll make the powders in Asia. I'm going to put it together in the US. I'm going to recycle it in Canada, you know, whatever it is. So you can, the labor costs change with that. The material costs may change. You have different transportation required. So the collection distances. What equipment are you using? What's the plant life? Things like that. The inputs are pretty easy. We tried to make it as easy to use as possible, but we balanced it between really getting down into the weeds and user-friendly. So we're somewhere in the middle. But basically, if you want to look at transportation, you can say from the end use to the collection point. So that's like from my house to Best Buy to the drop box, 20 miles, right? And collection to the recycler, well, we need to go to Ohio, and so it's going to be, you know, 1,000 miles, say. So you can enter all this stuff in. You hit go, and actually you can say this is going to be by car, this is going to be by truck, this is going to be by air, this is going to be by sea, or a combination thereof. Again, we have just default information in here. At any time, you can change the information because a lot of the times we don't know the answers, but you may have insight into, I know rail's not 5 cents, it's only 4 cents, so you can use that. There you go. Here's the simple output, and this is one example. As I said, you could compare your process to other recycling processes. It stacks them up right next to each other. This is the cost to recycle 1 kilogram of cell. For pyro, it's this much, hydro is this much, and these are generic ones, right? Of course, I don't have them here because all the people say, wait, my process is cheaper than that. Anyway, and then you can have your process in here. Or this could be, you could be looking at the manufacturing of the battery, the collection of the battery, the recycling of the battery, and say, wow, this is the big part of it all. There's also energy consumption and emissions. This is a truncated example, but you get the idea of the information that comes out of this. Oops. Okay, so finishing up just in time. We have some labs. We now have a total of 3 labs. This is a part of the Materials Engineering Research Facility at Argonne National Laboratory. So this is, you know, that's really an optimization and scale up. So we're developing new technologies, we're optimizing those processes and scaling them up. We have high bay space for larger equipment. We have bench scale equipment in labs. This is an old picture. And then we have other pilot scale, another pilot scale lab that I don't have pictured here. Let's see. One thing that I think is important to resell in general is what our job is, our goal is to come up with technologies that say, hey, direct recycling or whatever it is can benefit the United States and the energy securities that we need. But we don't do it in the real world. We rely on industry. And so we have been working from day one with industry to make sure that they're on board with what we're doing. Because we do a lot of cool stuff at the labs. I mean, it's really cool stuff. But if you don't connect it to industry, if you can't get them to figure out exactly what they can do with it, it's never going to really take off and go anywhere. So anyway, so we've been working with industry, and I'll leave it at that. These are all the people that are involved. Sam Gillard is the technology manager at the Department of Energy that I work very closely with. He's extremely into this, and it's great. Stephen Boyd and David Howell as well. So, and all the people at the different institutions. And we do have a website, resellcenter.org. There is resell@anl.gov, but if you want to get just me, you can email me. It's simple, jspangenberger@anl.gov. That was a joke. Actually, you can do Spang, SPANG, @anl.gov, and you can get a hold of me with questions. And that's the last slide, Beth. So, are there questions?
Great. Thanks for a really interesting presentation. Before we take questions, I'll remind our audience that you can type in your questions through the GoToWebinar toolbar, and I'll be reading those to Jeff. So our first question is, do you have any data on materials handling equipment such as forklifts, tuggers, AGVs, as well as construction/industrial equipment, excluding microgrids, in terms of percent of lithium ion versus other power sources?
That's good. That's good. Yeah, we haven't looked too much into that. I actually have a friend of mine that is in the fork truck business, and he says that lithium ion is starting to take off. The ironic part is they have to add counterweight because they're so light. Typically, right now, if it's electrically powered, it's going to be with lead acid batteries. So unfortunately, I don't have data on that, but I think that's an important sector that does need to be included in the verification of validation of this energy storage with lithium-ion batteries. So sorry, I don't have an answer for you, really.
Okay. So this one has sort of a three-part yes or no, and then if yes, section at the end. So
okay,
I'll go for it. So one, is part of your research to identify and map existing recycling facilities. Two, is part of your mission to develop model facilities with detailed site characteristics, building design parameters. And three, is part of your mission to incorporate startup recycling facilities. And if yes to any of those, could you speak to what you've discovered thus far regarding each?
Wow, great question. So the first one, what was that? Mapping out what's out there? Is that right?
It is identifying and mapping existing recycling facilities.
Yeah, okay. Actually, just recently, within the past month, we started to put together a map of all the different players that are out there. And it's kind of interesting because there are the players that are well-established companies that are saying, hey, we can use our technology to recycle batteries. But I think even more, there are startups that say, I have a great idea that's going to improve this recycling process, and so there's a lot of startups. So we're putting a map together. If you're interested, let me know, and I can probably share with what we have. But that's a work in progress, and that'll also be dynamic. Things will always change. Regarding a model facility, and I think that actually ties along closely with the part 3 on that one with startup facilities. Our goal, let's see, the plan is for the first 3 years, year 1 of resell, work at the bench scale level to kind of see what sticks, what's working, what's not. Year 2, start scaling up. And when I say scaling up, I mean small scale, like 1 kilogram batch stuff. For the more promising technologies that we have. Year 3 is to finish scaling up the technologies that are working so that we can demonstrate, though it would be ugly, a unit operation based process to go from a battery to a battery. And the focus right now is really cathode, but along that lines, we would also demonstrate our electrolyte salt recycling, things like that. The next step then is to say, and so that's almost like a choose your own adventure. Maybe you could say, I'm going to shred the battery. I'm going to go, I'm going to separate the anode and cathode powders using this technique. I'm going to relithiate the cathode powders with this technique, and I'm going to make a new battery. Or I'm going to shred the batteries, and I'm going to use a different separation technology. And this one's going to have electrolyte recovery. And so one may have 4 steps, one may have 7. You're going from unit operation to unit operation in the lab, but at the end of the day, you can demonstrate. So it's really research focused. So that's years 1 through 3. Years 4 through 6 is then taking that, streamlining it, scaling it up further. So perhaps we're doing 10 kilograms. I like to scale in factors of 10. So maybe we're doing 10 kilogram batches now, and we've really honed in the process to go, we're going to do it this way, this way, this way, and this way. And then the next thing is to scale it up to a more, even a higher, a larger scale. And every time we scale it up or we move forward, we get industry more and more engaged. If industry doesn't engage, we'll move on to something else. But we need industry to take this, and they need to get involved early on, as I mentioned. And so, yes, we'll have a model facility to recycle it. And we will, part 3, work with startups or any company that is interested in taking or combining our technologies with their technologies to establish commercial recycling facilities. Hopefully it answers all 3 questions.
Is there a worry that we won't have enough raw materials to meet the demand for the amount of batteries we will need in the coming decades?
Yeah. I guess my personal answer on that is no. We have the materials, the prices are going to go up, because if somebody knows there's going to be so much demand, they're going to produce it, and it's just going to cost more money because you're going to use worse, not as good of a mine, something like that. So I think we'll have the materials, the prices will go up for those materials to get them. That's my personal opinion. I don't think, and then it balances out. It's just too much money, so you get less demand. It's price and demand. So I don't think we'll reach that point.
Okay, the next one is, I have a question and a comment about the cobalt supply chain. I'm John Abelson. I teach materials for sustainability at U of I. And specifically, the larger fraction of the cobalt supply chain comes from extraction as an impurity from the nickel supply chain. What are the prospects for capital investment to increase the extraction process?
Oh, that's a great question. And that is unfortunately not my area of expertise, and I'm trying to educate myself, so I should probably come to your class. So there's co-production, right? Cobalt is commonly co-produced and not the main driver. So it's very complex how it works. I wish I knew the answer to this because I want to sound smart, but honestly, I don't. I don't quite understand it fully, but it is a very complex situation, how all those get produced together. So I apologize that I don't know the answer to your question, but I know that there are people at Argonne that would love to help you answer that question. So if you reach out to me, or somehow we can get connected, I can work with you on that. That'd be great, because then I'd learn, and that's awesome.
John says, thank you. Love to collaborate.
All right, great. Thanks, John.
Are you looking at the option of skipping this battery electric phase and going to transportation sources utilizing third rail and overhead cable electric vehicles and electric trains?
We're not. We had to carve out a scope of this program, and right now, so we're even focused on older battery technologies. We're not even looking, except for the manufacturing scrap, looking for advanced like lithium metal batteries. We also don't look at the second use. We just, we carved our scope out, and so that is not within the scope of the resale program. Again, the bigger picture, there are folks that are going to look at different technologies, different transportation technologies, and it's the answer is going to be mixed. That I don't think everybody may not have an electric vehicle, just like everybody doesn't have a gas vehicle now. Somebody said ice age, internal combustion engine is ice, so it'd be ice age vehicle. I love that. So yeah, no, we're not looking into that right now, but people are, again, at Argonne and around the National Lab System. And again, happy to talk to you about that if you have some questions.
You mentioned other countries using, I believe, lithium/iron batteries. What countries do this, and for what applications?
Yeah, I was referring actually to a couple of companies have come out and said that they're going to start using lithium iron phosphate technologies. Tesla is one of them. Recently, I believe I read that in Asia they're going to use lithium iron phosphate because it does lower the cost. It's cheaper, but you don't have because the energy density isn't there. Your vehicle doesn't go as far. And so it depends on the market, really, as far as where those would be used. And at this point, I don't see that being used anywhere in the United States.
That was the last question that came in, and we are close to the end of the hour. So what final thoughts would you like to leave us with?
Oh, geez. I guess the biggest thing to me is as I started getting the costs down for this battery recycling to work. If we have to pay money to recycle batteries, it makes it extremely difficult to make this sustainable. Just like our e-waste that we deal with, or the recycling, our curbside recycling, we pay for those services. I don't want to be in a situation where we have to pay for this service. If you put a piece of metal out at the end of your curb, at least if I do in the suburbs of Chicago, within 30 minutes it's gone because it has value and somebody's going to pick it up and take it to be recycled. If you do that now with a battery, lead acid, someone will pick it up because there's value to that. But if you put a lithium-ion battery out of your curb, it's just going to sit there, and that's not good. We want to be able to have incentives, and one incentives I always think of is money to drive that system so that it's a sustainable process, sustainable infrastructure.
Excellent, thank you. If we didn't get to your question or you think of something later, feel free to reach out to resale@anl.gov. So Jeff, thank you very much.
Hey Beth, I'll change that. Send it to spang@anl.gov. That'll come directly to me then.
Okay.
Okay.
Great. Thank you.